Let's investigate Shor's factoring algorithm. Consider a semi-prime number denoted by capital N. The prime factorization of this semi-prime number is given by P1 times P2. We want P1 and P2 to both be greater than 2. Suppose that n is an even number. If n is even, then we can express it as 2 times some positive integer k. But that would mean that 2 is one of the prime factors, and that contradicts this property over here. So n is not an even number. It is an odd number, and we can express that as an even number plus 1. So we have 2 times some positive integer k plus 1. So this tells us that we're dealing with an odd number. Another property that we're interested in is that these prime numbers have to be distinct. So that means P1 does not equal P2. So n cannot be expressed as a single prime number raised to some positive integer exponent alpha. If alpha is equal to 2, then we would have the square of a prime number. And we don't want squares of prime numbers. We don't want any powers of prime numbers, because then this would not be distinct. So we want these prime factors to be distinct. And we also want them to be greater than 2, so that we're dealing with an odd number. We've imposed a lot of restrictions on n over here. N has to be a semi-prime number. That means its prime factorization consists of 2 prime numbers. And we also impose the condition that those prime numbers have to be greater than 2, and we want n to be an odd number. So the fact that it's an odd number, that is related to this property over here. Now let's use Shor's factoring algorithm to find the prime factorization of an n that satisfies these properties. So we can write this like this. We have Shor's algorithm. So what are the inputs and what are the outputs? What are we putting into the algorithm, and what is the algorithm going to give us? So the input is n. N is this semi-prime number. But we want to exclude squares of prime numbers, and we also want to exclude any even semi-prime numbers. And now that we have this n, we're going to output the prime factors, P1 and P2. So we're dealing with a very specific scenario that has applications in cryptography and in cybersecurity. So that's why I've specifically chosen this scenario. We can also generalize the factoring problem to more general prime factorizations that have more than 2 prime factors. And we could also have these repeated prime factors. We could have powers on top of these primes over here. But we're putting a lot of restrictions on what this capital N can be. And that's because this problem over here of factoring n into 2 prime numbers, this is the basis of many cryptography schemes. And it underpins a lot of cybersecurity in the modern world. So now let's actually see how to implement Shor's algorithm to do this procedure. To do the reverse is very easy to do on a computer. We take 2 big prime numbers, we multiply them together, that's just integer multiplication, and then we get n. But doing the reverse process is a lot more computationally demanding. So that's why we have to come up with clever algorithms to try and crack this problem. The first step of Shor's algorithm, once we are dealing with this kind of situation over here, is to select a random positive integer, which I'm going to denote as a. And a needs to be such that it is between 1 and n, the number we're trying to factor. So this is the first step. we have to select a random positive integer a such that it is between 1 and n. So it has to be less than n, and we don't want it to be 1, and we don't want it to be a negative number. So we're restricting this to positive integers. There's going to be two scenarios if we pick a random a. Let's examine the first scenario. So the first possibility is if the greatest common divisor of a and n is greater than 1. Now, to compute the greatest common divisor, we can use Euclid's algorithm. This was known since the time of ancient Greece, and it's a very efficient algorithm for computing the greatest common divisor of two numbers. And if it turns out that the greatest common divisor of a and n is greater than 1, then we are actually done. We've performed the factorization problem. We can identify that P1 and P2, the prime factors of this semi-prime number n, are equal to the greatest common divisor of a with n and n divided by the greatest common divisor of a with n. So this procedure of finding the greatest common divisor of a with n, that actually gives us one of the prime factors. And we can call that P1. And then to find P2, all we have to do is take that prime factor and take n divided by that prime factor. And that divides P2 over here. And once we've done that, we can end the program. So this is the end of the program. But that's only if we have this scenario over here. The other option, so this is also a possibility, is if the greatest common divisor of a with n is equal to 1. Or in other words, a and n are co-prime. That's another way of saying this. So we have the greatest common divisor of our randomly picked a, and n is equal to 1. Well, if this is what's going on, then we're going to have to implement the order finding subroutine. So what does order finding mean? Well, I'll write this out explicitly. We need to find the minimum positive integer r such that a, that's our randomly selected value, a to the power of r is equal to 1 mod n. So we will elaborate on this property later in this video, but first we need to understand that this r is called the order. Specifically, r is the order of a mod n. And it is the minimum positive integer. And it's very important that we define it as the minimum. Because if we don't define it as the minimum, we're going to have some ambiguity. This is the part that is done on a quantum computer. So I'll put in brackets over here. This is the quantum part of Shor's factoring algorithm. And in order to actually do this, we have to execute the order finding subroutine. And that is the topic of another video in this cryptography and quantum algorithms playlist. So this is actually a fairly complicated procedure that involves utilizing the quantum Fourier transform. The Hadamard transform also appears, and we also have the concept of modular exponentiation. So we use that to find the order of a mod n. That is why this is called the order finding subroutine. Now let's assume that we have executed the order finding subroutine and we have the value of r for our randomly selected a. So given r, there are two possibilities. So let's examine those two possibilities. The first possibility is that r is even. So that means that 2 divides r. 2 divides r. This vertical line is notation for divides. That means 2 is a factor of r. Or in other words, r is an even number. We also need another property to be satisfied. So I'll put and over here. This is the Boolean logic symbol for and. We want a to the power of r on 2 to not be equal to minus 1 mod n. And we will elaborate on this property in a moment. So these are two properties that we want to be satisfied. We need r to be even, and we need a to the r on 2 to not be equal to minus 1 mod n. Now, if that is satisfied, then what we can do is identify that P1 and P2 can be computed by finding the greatest common divisor of a to the power of r on 2 minus 1 with n. So that's our P1, and then the P2 is the greatest common divisor of a to the r on 2 plus 1 with n. And I'll close these squiggly brackets over here. So this might work, but it might also fail. At this point in the procedure, there are several things that can go wrong. So if it does work, and we do successfully get P1 and P2, we can verify that by multiplying these positive integers together. And if we get n, this number n that we're trying to factor, then we have successfully verified and it works. And we can end the program over here. So successful factorization has occurred. But there's also another possibility. And the other possibility is that these conditions are violated. So if r turns out to be odd, or if this turns out to be an equality, if we have a to the r on 2 equals minus 1 mod n, then this algorithm will actually fail. So this part of the procedure is not going to work. So I'll put over here, we have else. So if we don't have these conditions, then we're going to have to restart the program with a new value of a. Or in other words, we're going to have to go back to the beginning, back to this starting step, and randomly select a different value of a, because we found that a does not work. So let's summarize this procedure over here. We're given with a specific number n. This is a semi-prime number, and the prime factorization consists of two distinct primes which are greater than 2. What we want to do is begin by selecting a random value a in between 1 and n. So we have an integer a. Now that we have this positive integer, we need to compute the greatest common divisor of a with n. If it turns out that this greatest common divisor is greater than 1, then we're done the factorization procedure. We can identify P1 as that greatest common divisor, and then we can take n and divide it by P1, and that's going to give us P2. So this is a very lucky scenario. It's not guaranteed that this is going to happen. In fact, it's more likely that we're going to end up with this scenario over here for an arbitrary large n. So it's more likely that a and n are going to be co-prime. And if they are co-prime, then we implement the order finding subroutine. So we need to find the minimum positive integer r such that a to the power of r is equal to 1 mod n. And we can efficiently do that on a quantum computer using the order finding subroutine. Once we have the value of r, we need to verify whether it is even and whether a to the r on 2 is not equal to minus 1 mod n. We need r to be even because we're going to be dividing it by 2, and we want to get an integer. If r is odd, then we're going to be dividing it by 2, and we're going to get a fractional power over here. And that's going to cause some problems. Another potential problem is if this value over here, a to the r on 2, is equal to minus 1. That's going to cause problems with computing the greatest common divisor and getting a prime factor. So we might actually not get the prime factors. If both of these conditions are satisfied and we successfully manage to find the prime factors by computing the greatest common divisor of these values with n, then we can end the program here. But if it doesn't work, then we know that this value of a is not going to work with Shor's factoring algorithm. So we have to go to this step, we have to restart with a new value of a. And that means we go back to the beginning. So effectively, this is a guess and check algorithm. We start with a guess, we see if it works. If it doesn't work, then we try and turn that guess into a better guess. So this value over here and this value over here, this minus and this plus value, they are actually better guesses than A. We are turbocharging this guess with a quantum algorithm. And if that guess doesn't work, then we have to restart with a new random guess. So this might not work with one run of the algorithm, but if you keep running the algorithm multiple times, you will, with a high probability, get the prime factors of n. So this is an overview of Shor's factoring algorithm applied to this specific semi-prime number. Let's elaborate on some of the properties over here. So first, let's elaborate on modular arithmetic. I'm going to draw a little circle down over here. So imagine we have a circle of numbers. We have 0, plus 1, plus 2, then dot, 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 all of the other intermediate values, and then we're going to get to minus 2 and minus 1. We can imagine that this is a circle, and it's going around. We have this kind of cyclic property. So 0 in modular arithmetic, it represents every integer that is an integer multiple of n. So here we have every integer multiple of n. And lowercase m is just some positive integer. It can also be a negative integer, and it can also be 0. So we can generalize this. This can also be minus n or minus 2n. All of these values are represented by 0. What about plus 1? Well, plus 1, it represents every integer multiple of n plus 1. You can think of this as a remainder after we do division. You can link this to the quotient remainder theorem. What about this plus 2? Well, that is every integer multiple of n plus 2. And over here we have every integer multiple of n minus 2. And then we have every integer multiple of n minus 1. So n minus 1 is the same as minus 1 over here. I'll write that out explicitly underneath. If we have n minus 1 squared, that's the same as minus 1 squared, and minus 1 squared, that's equal to plus 1. And this is valid mod n. So this is an example of manipulating integers using modular arithmetic. So I think this circle visualization is very useful because these values over here, they are just representatives of all of these different numbers that satisfy these conditions. So now that we have an understanding of modular arithmetic, let's have a look at this relationship over here. We're defining r to be the minimum positive integer. Why do we have to stress that it is the minimum positive integer? If we don't put minimum over here, there's going to be some ambiguity. So I'll show you what I mean by ambiguity. We mean that if we have a to the power of qr, where q is some positive integer, this is the same as a to the r raised to the power of q. And a to the r, by definition, is equal to 1. So then we have 1 to the power of q. That's 1 times 1 times 1. However many times we have q over here. So that means this is going to be 1. We're raising 1 to the power of a positive integer. And that gives us 1. And we need to write mod n because we're dealing with modular arithmetic. So this tells us that any integer multiple of r also satisfies this relationship. That's why we need to specify that we're dealing with the minimum integer r. And it has to be positive as well. That's why we have this condition over here. R is greater than 0. So r could be 1. That is a possibility. But in general, it's more likely it's going to be some large positive number if n is really big. So this is an explanation as to why we have to specify that it is the minimum value. Another important relationship is if we take this 1 over here and we move it to the other side, or in other words, if we subtract 1 from both sides, we get the relationship a to the r minus 1 is equal to 0 mod n. So this is another way of stating this relationship over here. What does this tell us? it tells us that a to the r minus 1 is an integer multiple of n. Remember that 0 over here, 0 is a representative of all integer multiples of n. So the remainder is 0. You can actually think of this as mn plus 0. So that is the remainder that we're dealing with over here. Whereas the remainder is non-zero for all of these other values. So that is what this statement is telling us. And another important thing that we can observe is that r on 2 is less than r. So half of r is less than r. That implies that a to the r on 2 is not going to satisfy this relationship. So that means this is not going to equal 1 mod n. And we can move the 1 to the other side just like we did over here. And that's going to give us the relationship a to the r on 2 minus 1 is not equal to 0 mod n. So the reasoning over here is that r has to be the minimum positive integer such that this relationship is satisfied. And r on 2 is less than that minimum, so it is impossible for r on 2 to satisfy this relationship. And we can just manipulate that relationship by subtracting 1 from both sides, and that gives us this relationship. Now, let's see where these factors are coming from over here. So let's take a to the r minus 1. We can rewrite that as a to the r on 2 squared. You can see that this square cancels with this half. So that gives us back to what we started with over here. And then we have minus 1, and we can identify this as the difference of squares. We can rewrite it as a to the r on 2 minus 1 times a to the r on 2 plus 1. So that's what we're dealing with over here. And we know that this is equal to 0 mod n. So in other words, when we say something's equal to 0 mod n, we're saying it is the same as a integer multiple of n. So we have two factors that multiply to give an integer multiple of n. And if we take these two factors and then we compute the greatest common divisor, that gives us a really good chance of finding P1 and P2. But this might not work. What are some problems that could arise over here? So the first problem is if r is odd. If r is odd and we divide by 2, we're dealing with a fractional power, and that's going to cause problems. We want this to be an integer. We need r on 2 to be a positive integer. Another problem that could arise is that one of these values can be equal to 0. Or in other words, one of these values could be an integer multiple of n. And that's going to cause problems. If we look at this first value over here, so imagine this first value is the one we're interested in. This reasoning over here prohibits it from being equal to 0. So a to the r on 2 minus 1, that is not equal to 0. But what about this value over here, where we have a plus instead of a minus? This is where we could run into some problems. Now, let's examine where the problem could come from. So we're asking the question, is this equal to 0? We want it to be non-zero for the algorithm to successfully work. So we need a to the r on 2 plus 1 to not equal 0 mod n. Now, if we move this 1 to the other side by subtracting 1, what is that going to do? Well, that's going to give us a to the r on 2 is not equal to minus 1 mod n. And have a look at this condition. This is exactly the same condition that we have up here. So that's why we want to verify that this is not equal. So we don't want a to the r on 2 to equal minus 1 mod n, because that's going to cause problems. The problems it's going to cause is that we're going to have something that is an integer multiple of n on the left-hand side. But we don't want any integer multiples of n inside these factors over here. We want this to be something different from 0, and we want this to be something different from 0. But we want their product to be equal to 0. And that's going to allow us to successfully compute the prime factors. So this is an overview of all the number theory that we're dealing with in Shor's factoring algorithm. But we haven't yet touched on the quantum mechanical part. So the quantum mechanical part of Shor's factoring algorithm comes into play over here. It is the order-finding subroutine. And the order-finding subroutine is the topic of the next few videos in this quantum algorithms playlist.